We're now moving on to 16.3, the second and third laws of thermodynamics. In this section, we're going to state and explain the second and third laws of thermodynamics and calculate entropy changes for phase transitions and chemical reactions under standard conditions. So, we first need to understand the terms system and surroundings. So the system is the part of the universe that is what we're looking at. It's what we're interested in. So then your surroundings is the rest of the universe outside of the system. So you really get to determine what you are focusing on for your surroundings and system. You could have the universe as your surrounding and the earth as your system. Nonetheless, your system is in your surroundings. So to predict the spontaneity of a process requires us to consider entropy changes in both the system and surroundings. So one thing that we might say is that the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of our surroundings, or the surroundings. So the change in entropy of the surroundings is directly proportional to the change in enthalpy of the system. Good old delta H. Enthalpy comes along all the time. And the change in enthalpy, change in entropy of our system, or surroundings, is also inversely proportional to the temperature. So we could say that delta S, delta entropy surroundings, is equal to negative delta H, or enthalpy of the system, divided by your temperature. Now let's consider a system. Oops. Where we have two objects and we have some heat flowing. So we have our surrounding object, and then in it is our system object. And so we have some heat flowing between the two. Okay, so we have some Q surrounding and some Q system. So we're getting some heat exchange going on. So let's go ahead and say that the hotter object is the system. So that means the system, since heat flows from hot to cold, is giving its heat off to the surroundings right now. So this is my first, one of our processes we're going to look at. Okay, so one, the Q system is higher than Q. Whoa, that's a weird looking Q. Than Q surround. So what this ends up telling us is that our change in entropy of the system is equal to the negative Q of the reversible process over T. And then the delta S of our surrounding is equal to the Q, or heat, of the process of the reversible process divided by the temperature. So remember, enthalpy and heat are directly related to each other. Because here we're saying that the temperature of our system is greater than that of our surroundings. So here, the entropy decrease of our system is less than the entropy increase of the surroundings. So the surroundings are increasing in entropy. We're adding energy to it. So now the surrounding, since that is outside of the system, or it's what the system is contained in, so since the entropy of the system, or the surroundings, is going up, then the entropy of the universe will increase. So, okay, so that's the first one. That would be increasing the entropy of the universe. The second one, we're going to say the objects are at different temperatures. Heat is going this time from the cooler object to the hotter object. Now, this never has been observed to happen spontaneously. Okay, so Q of the system is still greater than Q of the surroundings. But this time, delta S of the system is gaining Q, so it's equal to positive Q over T, and delta S surrounding is equal to negative Q over T. Now, because of that, the system, let's see, is gaining heat. The surrounding is losing heat. The surroundings are going to have a greater change, a greater magnitude of change in entropy. But because of the sign of that negative Q, so it's losing that heat though, overall the entropy of the surroundings is decreasing, making the entropy of the universe decrease. And then our third scenario is our objects are about the same temperature. So system and surrounding are the same temperature. And so the magnitude of the entropy change for both of them are essentially the same. So in this case, the entropy change of the universe is 0, and the system is at equilibrium. If anyone's looking at these notes, they're probably just, without watching or listening to the lecture, they're probably going to be really confused. But hey, rewards for those of you actually listening to the video, right? So, like I was just kind of hinting at, the entropy change of the universe is the sum of the entropy changes for the system and surroundings. And then we can use the equation for delta S surroundings of Q surrounding over T to give us this delta S universe is equal to delta S system plus Q surroundings over T. And all this comes down to the second law of thermodynamics, which tells us that all spontaneous changes cause an increase in the entropy of the universe. Okay, so that means delta S universe is positive, but keep in mind that if you have a process with a negative delta S of the system, you can still have a spontaneous process if delta S of your surroundings is greater than delta S of your system. So even if you have a negative delta S system, if the change in entropy of your surroundings is greater than your change in entropy of your system, you can still have a spontaneous process. So again, when delta S of the universe is greater than 0, you're spontaneous. Less than, it's non-spontaneous, but the reverse direction of that process is going to be spontaneous. And if delta S equals 0, you're at a process at equilibrium. So let's look at an example. Will ice spontaneously melt? So we're told the entropy change for the process of solid water going to liquid is 22.1 joules per Kelvin, and it requires that the surroundings transfer 6 kilojoules of heat to the system. Is this process spontaneous at negative 10 degrees Celsius? And what about at positive 10 degrees Celsius? So remember, delta S universe is equal to delta S system. And we're just going to go ahead and use plus Q surroundings divided by our temperature. Well, technically this is plus negative Q surrounding, or negative Q reverse. And we'll just go ahead and use plus Q surroundings over temperature. Yeah, because that's the same thing. Okay, so we're told that delta S system is equal to 22.1 joules per Kelvin. And then at negative 10 degrees Celsius, Q surround, which we're told the surrounding, we're transferring 6 kilojoules, so that's negative 6.00 joule times 10 to the third joules. Okay, and we're doing this one at negative 10 degrees Celsius, which means we need to add 273.15 to make it into Kelvin. So this is divided by 263.15. So delta S of the universe for this first part equals 22.1 joules per Kelvin plus negative 6.00 times 10 to the third joules divided by 263.15 Kelvin, and that ends up getting you negative 0.7 joules per Kelvin, which is less than 0. So this is not spontaneous at negative 10 degrees Celsius. Now let's do this at positive 10 degrees Celsius. So our delta S of our system is going to equal 22.1 joules per Kelvin plus negative 6.00 times 10 to the third joules divided by, this time is 283.15 Kelvin. And that gives us positive 0.9 joules per Kelvin, which is greater than 0. So yes, this one actually is spontaneous. So the melting would be spontaneous at 10 degrees Celsius. And this makes sense, right? Because at negative 10 degrees Celsius, we're below the freezing point of water. So it's not going to spontaneously melt because it's below its melting point, freezing point. Whereas at positive 10, we're above 0. So we are above our melting point. So this brings us to the third law of thermodynamics. So the entropy of a pure, perfect crystalline substance at 0 Kelvin is 0. So 0 Kelvin is called absolute 0. And at absolute 0, there's no temperature lower than it. It's never been achieved in a lab. It's basically impossible to achieve. They've come very, 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 very close. May as well be 0 Kelvin, but it actually technically isn't. All molecular movement completely stops at 0 Kelvin. So even in a solid, the molecules are still vibrating in place. All that stops. And there's literally only one possible way to arrange the molecules. Okay, so we also do have a thing called standard entropies. So it is possible to determine the absolute entropy of a substance. And we start off by using standard entropies, or S naught, S standard, whatever you want to call it. And these values are for 1 mole of a substance at a pressure of 1 bar and a temperature of 298 Kelvin. And if you have an aqueous species, this is at 1 molar concentration. So appendix G has values. So if you're doing your homework or taking your exam, use the appendix for values when you need them. We can use standard entropy values to calculate standard entropy change, or delta S naught, for a process. Your book does give you a mini chart, if you will, of some substances, but there is a much bigger one in the back of your book in the appendix. You can also look them up as well. So if you remember Hess's law, I think was that like chapter 6 or something, delta H, so the enthalpy change of a reaction, is equal to the enthalpy change of the products total minus the sum of the enthalpy change of the reactants. Very similar for entropy, it's equal to the sum of the entropy of the products minus the reactants. But also don't forget to multiply the standard entropies and or enthalpies of formation by the coefficients of the balanced equation. So don't forget, if you have a 2 in front of it, you need to multiply by 2. So let's go ahead and do an example. We want to calculate the standard entropy change for the process of water going from a gas to a liquid. So we're going to go ahead and look in our chart, and we find that delta S0 is equal to products minus reactants, and then there's just one for the coefficients in front of each of the waters, so we don't have to worry about that, but that's what we're just going to go ahead and put 1 mole here. So times my product, which is liquid water, and it has a standard entropy of 70.0 joules per mole, or joules times inverse mole times inverse Kelvin. So you can see our moles cancel and we get joules per Kelvin, minus 1 mole times the standard entropy of our reactants, which is 188.8 joules per mole per Kelvin. And again, moles cancel. And so this comes out to be negative 118.8 joules per Kelvin. So this is a negative delta S. So this, if you recall, is not spontaneous, which makes sense, right? It's not a going from gas to liquid is not a spontaneous process. So here's another example. This one we're looking at the combustion of methanol, and they were nice enough to give us the balanced reaction. So delta S standard is equal to the sum, and we're going to go ahead and just put a little symbol there to represent the coefficients of the standard products minus the sum of our coefficient times our reactant. So let's go ahead and start with our products. We have 2 moles for carbon dioxide, and its standard entropy is 213.8 joules per mole Kelvin. Sitting here lecturing and I hear my foster mama cats doing, I don't know what they're getting into, but I hear a lot of crinkling and they're in a whole different room. Okay, and then we also have 4 water, so we have 4 plus 4 times the standard entropy of water, which is 70.0 joules per mole Kelvin. So we can see our moles cancel. Let me just rewrite this, plus 4 moles. Moles cancel. And then that is going to be minus, from our reactant side, we have 2 methanol, so we need to have 2 moles for the methanol times its standard entropy, which is 126.8 joules per mole Kelvin. Plus oxygen, and that has a 3 in front of it, so we have 3 moles times 205.03 joules per mole Kelvin. Squeeze that in there and make it fit. There we go. And so then this all adds up to negative 161.1 joules per Kelvin for the standard entropy change for this reaction. So again, this is not spontaneous, but that means that the reverse would be spontaneous.